All right, today we're going to get into a hidden battle that's brewing inside the whole AI revolution. It's this surprising clash between tech progress and, well, the very communities that tech is supposed to be helping. We're calling it the data center dilemma.
So, we're all seeing this massive AI boom happening, right? But what's really interesting is that there's this quiet resistance building up. And that brings us to the big question for today. Why on earth are politicians, and we're talking from both sides of the aisle, suddenly trying to pump the brakes on the huge data centers that power all this AI?
And to really get a handle on this story, which is becoming a national issue, we've got to start in one specific place, New York State, and a pretty controversial bill that just got proposed there. Okay, let's dive right into the epicenter of this whole thing. New York. They're talking about a 3-year pause, a moratorium, and it's sending some serious shockwaves through the tech world. So, what's in the bill? Well, it's actually pretty simple, but wow, is it powerful. It's proposing a 3-year complete stop on any new data center permits. That means freezing both the construction of new ones and the operation of any that would come online. The sponsors are Democrats, State Senator Liz Krueger and Assemblymember Anna Kellis. And the thinking behind it? Senator Krueger puts it pretty plainly. She says the state is completely unprepared for just how huge these projects are. So this pause is really about giving them some breathing room, a chance to come up with smarter rules and avoid a situation where everyday people get stuck with insane utility bills down the road. But here's the kicker. This is not just a New York story, not at all. What's happening in Albany is basically a preview of a much bigger national trend that's really starting to pick up steam all across the country. Yeah, it turns out all those concerns being raised in New York are starting to echo in state capitals from coast to coast. This debate is going national, and it's happening fast. So just how widespread is this? Well, believe it or not, New York is just one of at least 6 states where lawmakers are seriously thinking about hitting pause on new data centers. This isn't some isolated thing. It's a real national debate. And just take a look at this list. The thing that really jumps out is how politically diverse it is. You've got Democrats pushing for these pauses in places like New York, Georgia, Vermont, and Virginia. But then you also have Republicans introducing similar bills in Maryland and Oklahoma. I mean, how often do you see that kind of agreement? And that leads us to what is frankly the most surprising part of this whole story. This totally unexpected bipartisan alliance that's pushing back against the nonstop growth of data centers. So on one side, you have one of the most well-known progressives in the country, Senator Bernie Sanders. He's actually come out and called for a full-blown national moratorium on building any new data centers. Then you jump all the way over to the other side of the spectrum, and you've got conservative figures like Florida Governor Ron DeSantis. Now, his reasons are different. He's tying data centers to higher energy bills and what he sees as the negative social impacts of AI. But his conclusion is basically the same: deep skepticism about letting them grow without any checks. I mean, this coalition is just wild when you think about it. It's bringing together the political left and the political right, plus more than 230 environmental groups. We're talking big names like Food and Water Watch and Greenpeace. They're all on the same page, calling for a national pause. So what is going on here? What's actually driving this sudden bipartisan backlash? Let's unpack the real concerns that are fueling this movement and take a look at what people are calling the price of progress. It really boils down to this kind of domino effect. So first you have the AI boom, which needs these gigantic data centers. Second, those centers use an absolutely staggering amount of electricity. That in turn puts a huge strain on local power grids and, of course, the environment. And the final domino, studies are now showing a direct link between all that power consumption and higher electricity bills for the people who actually live there. And all of this leads us straight to the heart of the conflict. It's a true balancing act, this whole AI situation. It's a search for some kind of path forward that allows for new technology without wrecking community well-being. Back in New York, you can really see the two competing ideas for how to handle this. On one side, you have the pause, that 3-year moratorium we've been talking about, which is designed to just buy some time to figure things out. But on the other side, you've got the plan. That's Governor Kathy Hochul's Energize NY Development Initiative. Her approach is to manage the growth by upgrading the power grid and forcing these data centers to, as she puts it, pay their fair share. So, we're left with this huge, fundamental question for the digital age we're living in. As the virtual world of AI keeps making bigger and bigger demands on our physical world, how do we find the right balance?
How do we innovate and push forward without leaving our communities in the dust? That's the tough spot that states all over the country are in right now. And whatever they decide is going to shape the future of tech, our energy, and our society for years to come.
All right, let's get right into it. So picture this. You've got a legendary mathematician, a total giant of the 20th century, who leaves behind this mountain of unsolved problems. Then, on the other side, you have a cutting-edge AI, one of the most powerful we've ever seen. This is the story of what happens when that machine tries to climb that mountain. So, what happens when you pit a super powerful AI against 700 of math's toughest open problems? That's the huge question here. A team of researchers basically unleashed this AI agent to systematically go after 700 unsolved conjectures from the famous Erdős problems database. And this wasn't just some casual test, It was a full-blown experiment to see if AI could really discover new math on a massive scale. And the challenge itself, it comes from Paul Erdős, who is, one of the most prolific mathematicians ever. He left behind this incredible legacy, hundreds and hundreds of unsolved conjectures. You can almost think of it like a giant scavenger hunt for mathematical truth, where the clues are just scattered across decades and decades of research.
Okay, but here's a really important thing you got to understand. When mathematicians say a problem is open, it doesn't always mean it's impossible to solve. A lot of the time, it just means you can't find the answer with a quick Google search. This creates this really interesting gray area where solutions might be hiding in plain sight, buried in some obscure paper from way back when. And that's exactly where an AI could have a huge advantage.
So, let's meet our AI hero, if you will. Its name is Alethea. It's a specialized math research agent built on top of Gemini. And its mission was simple but massive. Go through all 700 of those open problems and do the one thing humans struggle with: process, analyze, and spit out potential solutions at a completely insane speed. But listen, this wasn't just about letting an AI go nuts on a bunch of problems. No, the process was actually a really smart partnership. First, Alethea would generate a ton of solutions. Then, a second AI, a verifier, would come in and automatically filter all those results, looking for anything that might be correct. And only then, after all that, did a team of human mathematicians jump in to look at the best of the best. It's a true human-AI team-up right from the start. Okay, and this is where the story gets really, really interesting. Out of 700 problems, how many do you think the AI actually solved? You might be thinking it's a huge number, right? Well, the reality was, this intense filtering process that tells us something fascinating about what these AIs are really good at. So, we start at the top of the funnel, a massive list of 700 problems, all officially labeled open. Alethea's job? Take a crack at every single one. All right, first pass done. Alethea's own internal AI verifier makes the first big cut. It just throws out hundreds of attempts that are obviously flawed, leaving 212 responses that it flags as maybe correct. That's a huge drop, but still way too many for people to check one by one. Okay, now the humans get involved. The experts dive into that pool of 212 candidates, and wow, they find that only 63 are even technically correct. Turns out a lot of the AI's initial ideas were just plain wrong, or it had completely misunderstood what the question was asking. And then the final cut. After the real domain experts went through everything with a fine-tooth comb, that number plummeted to just 13. 13 solutions that were actually meaningful and correct. Think about that. We went from 700 all the way down to 13. That is some serious filtering. So why such a dramatic drop-off? Well, when you look at a sample of about 200 of the AI's candidates, a whopping 68.5% of them were just fundamentally flawed. It just goes to show, the AI was generating a ton of noise along with that tiny bit of signal. And this really gets us to the main takeaway of the whole experiment. Alethea didn't act like some genius mathematician, having brilliant flashes of insight. It acted more like a research assistant on steroids. It was just an incredibly powerful tool for sifting through mountains of information, spotting existing work, and flagging things that were worth a closer look from a human. So, what about those 13 that made it through? What did the AI actually do to solve them? The researchers broke it down into this really cool taxonomy of discovery. Yeah, just take a look at this breakdown. The most surprising thing here? The huge majority of these so-called successes weren't new discoveries at all. Only 2 were genuinely novel solutions. The other 11? They were either partial solutions or, and this is the big one, the AI was just finding answers that were already out there, just lost in the literature or too obscure for people to track down easily. And you've got to understand the difference here. It's pretty important. In 4 cases, the AI came up with a solution all by itself, only for the human researchers to discover, oh wait, someone else actually solved this years ago. We're calling that independent rediscovery. But in 5 cases, it was even more direct. The AI basically acted like a superpowered search engine and just found the obscure paper with the answer already in it. That's literature identification.
But there was one moment of what you might call pure AI creativity, a genuine spark. It was the solution to problem Erdős-1051. The researchers said the AI's method was totally new. It didn't look like any known human approach. So in this whole ocean of rediscovery, this was one small but really significant moment of actual machine invention. Of course, using these incredibly powerful new tools brings a whole new set of problems. And what this experiment really showed is that the hardest part of doing research with AI often has absolutely nothing to do with the math.
Yeah, the real bottleneck wasn't solving some crazy complex equation. It was all the detective work. The human experts spent most of their time just trying to figure out when the AI completely misunderstood the question, or digging through old archives to check if a new solution was actually just hiding in some paper from 1981. They were constantly wrestling with ambiguous symbols and definitions. This is kind of the hidden cost of collaborating with AI.
And this led them to a really critical warning. See, because these models are trained on, well, basically the entire internet, they can just spit out information they learned during training without telling you where it came from. So it might solve a problem just by perfectly recreating a solution it saw somewhere, but it never cites the source. The researchers have a great name for this: subconscious plagiarism.
So, what's the big picture here? What does all this mean for the future of science? Let's put these results into a little context. So, Alethea's 4 genuine contributions, the novel and partial solutions, that's a big deal. But it's also part of a much bigger trend. Other AI projects have already knocked down another 6 of these problems. You can really see a clear pattern here. AI is slowly but surely chipping away at this huge mathematical mountain.
When you boil it all down, this experiment really shows that AI is amazing at grabbing all the low-hanging fruit. Solving the problems that are open, simply because the answer is buried or obscure, not because they're insanely difficult. It's a huge accelerator for science, for sure, but it absolutely cannot do it alone. It still needs human experts to steer it in the right direction, to double-check its work, and to find that one tiny, crucial signal in a giant sea of noise.
So this is where we land. What this all shows is that the whole conversation is changing. It's really not a question of if AI can contribute to science anymore. That ship has sailed. The real question, the one we all have to figure out now, is how can humans, build the best possible partnerships with these new tools to unlock the next great wave of scientific discovery?
All right, I've got a paper here with a claim that sounds, completely out of science fiction. The idea is you can teach a huge, complex AI model how to reason by changing just 13 of its parameters. No, that's not a typo, just 13. So how on earth is that even possible? Let's get into it. So we're going to kick things off by treating this whole thing like a puzzle. Because honestly, the main takeaway from this paper, it just feels like an impossible trick that we need to figure out. Just look at that number for a second. 13. That's it. Researchers from Meta, Cornell, and Carnegie Mellon are saying that's all it took. That's the number of parameters they had to train to get a huge boost in an AI's ability to solve tough math problems. Just 13 little tweaks to teach it a whole new skill? It's wild. And yeah, that brings us right to the big question, the one we're going to try to answer here. How in the world can you actually change the behavior of an AI that has 8 billion different knobs to turn by just fiddling with 13 of them? Seriously, that's like trying to steer a giant aircraft carrier by just tightening one little screw. It just doesn't seem possible. Okay, so to really get why this is such a revolution, we need to take a step back and look at how things used to be done. The old way, because it's that context that makes the number 13 so absolutely mind-blowing. So the best way to picture a large language model is to think of it like a giant control panel, right? And it's got billions of these tiny interconnected knobs. Every single parameter is one of those knobs. And for the longest time, training or fine-tuning the AI meant you had to go in and painstakingly tweak massive groups of these knobs, just trying to get the output you wanted. And this table here, it really lays out the scale of what we're talking about. You've got full fine-tuning. That's the old school, brute force way, adjusting all 8 billion knobs. Then something much better came along called LoRa. This was way more efficient, kind of like just adjusting a few key sections of the control panel, but you were still messing with millions of parameters. And then you have Tiny LoRa, the new method from this paper. And that's like finding out this whole gigantic control panel can be controlled by a few secret master knobs. That's the incredible jump in efficiency we're looking at. So, the big question is, how did they find these master knobs? Well, that brings us right to the breakthrough method these researchers came up with. They call it Tiny LoRa. All right, first, let's quickly cover the foundation this is all built on. LoRa, which stands for low rank adaptation, was already a huge improvement. The big idea was, instead of messing with the original knobs, you cleverly bolt on a small new set of controls. They're called adapter matrices. These could change the model's behavior, and it slashed the number of parameters you had to train from billions all the way down to millions. A pretty big deal. Then came the next step in the evolution, LoRa XS. And this is where things get really interesting, because it made a critical change in thinking. Instead of adding new controls, it started asking a different question. What if we could just learn to better recombine the most important settings the model already has? That was a huge insight, right? The power's already in there. You just have to figure out how to conduct the orchestra. And that, finally, brings us to Tiny LoRa. This is the really radical idea. It takes that whole recombination concept and pushes it to the absolute extreme. It figures out how to learn a single tiny little vector, we're talking sometimes just one number, that acts like the master controller for putting together all those powerful, pre-existing abilities inside the model. So how does this actually work in practice? Well, it's basically a four-step recipe. First, you look inside the AI and find its most powerful, most important settings. Second, you create that tiny, trainable vector, and that's where our 13 parameters live. Third, you use a fixed random matrix to kind of blow up that tiny vector into a full-sized instruction sheet. And finally, number 4, you use that instruction sheet to tell the model exactly how to mix and match its existing skills to solve the new problem. But, just coming up with the method is only half the story. The other, maybe more important half, is why it works so ridiculously well. And the secret ingredient, as it turns out, isn't just about how you teach the AI, it's about the whole philosophy of the lesson itself. Okay, these two charts right here, this is the absolute heart of the paper. On the left, you've got reinforcement learning, or RL. On the right, supervised fine-tuning, SFT. Now look at the bottom axis. That's the number of parameters we're training. See that chart on the left? With RL, performance just rockets up to over 90% with just a tiny handful of parameters. Now look at the one on the right, SFT. You need hundreds of thousands, maybe even millions of parameters to even get in the same ballpark. It's a night and day difference. So, what is the big difference here? Well, think of it like this. Reinforcement learning is like teaching a dog a trick. You just give it a simple reward signal. Good dog if it gets it right. Nope, try again if it's wrong. The AI tries to solve a problem, and all it gets is a thumbs up or a thumbs down on the final answer. The signal is simple, but it's super clean. Supervised fine-tuning, though, that's more like forcing the AI to copy your homework word for word. It has to memorize every single step, including your specific writing style, your phrasing, all the junk that doesn't actually matter for the answer. So the signal is dense, sure, but it's also incredibly noisy. And the researchers themselves put it perfectly. They basically say that with SFT, the model gets confused. It can't tell the difference between the important logical steps and all the stylistic fluff. So it wastes its very limited learning budget on both. But with RL, all that noise is gone. It gets a pure, clean signal about the one thing that actually matters. Did you get the right answer? All right, so this is a really cool technical trick. No doubt about it. But so what? What does this actually mean for the real world? Why should you and I care about this kind of extreme efficiency? Now check this out, because this chart shows something that is completely counterintuitive. I mean, you would think a bigger, more complex AI would need more tweaking to learn something new, right? But what this research found is the complete opposite. As the base model gets bigger, that's the bottom axis, the number of parameters you need to teach it something new actually goes down dramatically. It turns out bigger models are somehow easier to program with these tiny little updates. It's wild. So what does this mean in the real world? Well, this level of efficiency is a total game changer. We're talking about radically lower costs for training.
It paints a picture of a future where one server could host thousands of different personalized AI models, one for every single user, because each personality is just this tiny little file. This could also be a huge step in solving catastrophic forgetting, where AIs forget old skills when they learn new ones. And ultimately, it just makes powerful AI customization accessible to way more people.
Okay, and that brings us to our final thought. Let's zoom out from all the technical stuff for a second, because this research really forces us to ask a much bigger, more fundamental question.
And his quote from the paper is the perfect place to leave things. Think about it. How is it even possible to learn a complex skill like mathematical reasoning in just 13 parameters? Well, the authors float this mind-bending idea. Maybe the model isn't learning the knowledge at all. Maybe the knowledge to solve the problem is already in there, buried deep inside its billions of parameters from the get-go. And maybe this whole fine-tuning process isn't about teaching it what to do, but just changing its style. Maybe it's just nudging it to give longer, more step-by-step answers, which in turn unlocks a reasoning ability ahead all along. So I'll leave you with this question. What does it really mean for an AI to learn something new? All right, let's jump right in. What if the best way to make AI smarter wasn't to build one single, giant, super expensive brain, but instead to create a competitive marketplace where a whole team of different sized AIs could bid for jobs? Well, that's exactly what we're breaking down today. A really fascinating new paper from Meta's Superintelligence Labs. But first, before we get into their wild solution, we really need to get a handle on the problem they were trying to solve. And it's a problem that's at the very heart of a huge debate happening in the AI world right now. There's this big idea gaining a lot of steam that these smaller, cheaper, way more efficient AI models are getting so good that honestly, they might be all we need for most everyday tasks. The whole era of these giant, power-guzzling models, maybe it's coming to an end. So, to put this to the test, the researchers took a whole family of AI models, or agents, as they call them, of all different sizes. Everything from a small 4 billion parameter model all the way up to a much beefier 32 billion parameter one. You can really think of them like a team of freelancers, from the eager junior developer to the super expensive senior expert. And it's a nice thought, right? But as this research shows pretty clearly, that optimism, well, it runs smack into a big problem when things start to get complicated. Now, check this out. What's so interesting about this chart is how it shows exactly what happens when you give these agents harder and harder stuff to do. Over on the left, for the simple tasks, see those light-colored lines all bunched up at the top? Everybody's doing pretty well. But now look to the right. As the tasks get more complex, those dark purple lines way down at the bottom, this huge gap just opens up. The small AIs, they just can't hang. And the numbers? The numbers really drive it home. On the easy stuff, the smallest little agent is performing almost as well as the biggest one. But on the toughest challenges, its performance just falls off a cliff, hitting only about a fifth of what the big model can do. That's not a gap, that's a chasm. And this kind of backs us into a corner, doesn't it? Do we have to stick with the cheap AIs that are limited, or are we forced to shell out for the powerful, expensive models every single time, even for the simple stuff? Okay, this is where the paper gets really clever. Instead of choosing one or the other, it proposes a whole new system, and it's inspired by something we all get, a freelancer marketplace. They call it SAIL. It stands for Strategy Auctions for Workload Efficiency, and the core idea here is really simple. Let's turn the whole problem of assigning tasks into a competitive auction. Seriously, just picture a job board. A new task comes in, and instead of just handing it off to the biggest AI, you let all of them compete for the gig. Here's how it works. First up, bidding. All the agents submit a short plan, their bid, saying how they'd tackle the problem. Then, scoring. A jury of other AIs scores each one of those plans, weighing how good it is against how much it's going to cost. Then, the system makes its selection, picking the winning bid, the one that offers the best bang for the buck. But this last part is the real genius move, improvement. The cheaper agents who lost the auction actually get to study the winner's plan, which helps them learn and make better bids next time around. It's a built-in learning mechanism. So, the big question is, does all this cleverness actually work? Does creating a competitive AI economy actually lead to better results? Well, the numbers are pretty mind-blowing. Right off the bat, the total cost of getting all the work done dropped by 35%. That's a huge saving. And it managed to do that by being way smarter about who does the work. The system ended up cutting its reliance on that most expensive AI agent by more than half. But this This is the real kicker. This system wasn't just cheaper to run, it was actually more accurate than if you had just used the most powerful, most expensive AI for every single task. This chart just illustrates that result perfectly. See all those dots? Each one is a single AI agent, showing its performance versus its cost. But that blue star? That's the sale auction system. It completely carves out this new sweet spot. It's achieving higher performance than any single agent could, but at a much, much lower cost. It really is the best of both worlds. So when you take a step back and look at this, you realize it's not just some clever technical trick. It really suggests a fundamental shift in how we might think about building and using AI in the future. The paper itself puts it perfectly. Maybe the future of AI progress isn't this endless race to just build bigger and bigger models. Maybe it's actually about designing smarter systems that coordinate the models we already have in better ways. Ultimately, the whole goal shifts from just finding the one strongest agent to actually building the most efficient and intelligent team possible. And that leaves us with this really provocative thought to chew on. What if we've been thinking about AI all wrong? What if the path to greater and greater intelligence isn't about building a single monolithic god in a box, but instead, it's about cultivating a vibrant, competitive, and constantly learning economy of agents?